In order to look at the mathematics behind universal gravitation and gravitational fields, um, we're required to kind of go and look at the concepts again. Now, the good news is that the concepts are not too difficult. The math can be a little bit confusing because everything we're about to speak about is based off of the same universal gravitation equation that Newton helped to derive, but they're all slight variations. So I'm going to try and explain in the simplest terms possible how these are all related to one another and how conceptually while the math can seem kind of complicated and maybe convoluted at times, it's fairly straightforward and it is all based off of this one governing equation. Just to make sure we're all on the same page, we all need to be aware that gravity, as we know it, is not just the Earth pulling down on our bodies. It's actually the attraction between any two masses, or any three or four. It's the attraction between any masses to other mass in the universe. The most fascinating part about all of this is that nobody actually knows why gravity exists or what it actually is. So we don't know why when we jump up the Earth pulls us down. We don't know why the mass of the sun attracts the mass of the planets and keeps them in orbit. Nobody really knows why. There's some interesting theories, and there's been some research done lately that may be moving in a certain direction, but essentially nobody knows why. It's kind of the big unanswered question in all of physics. Regarding the gravitational fields that we've been analyzing in class, there's only two things that we're going to take a look at. The first being the force that field would exert on particular objects that have mass, and the second would be the potential energy that those masses might contain when placed in the field. Before we get to all the mathematics behind that, though, we do have to clarify one point that we didn't really speak of up until now. We've seen examples like this, such as the classroom, and examples like this, such as a planet or Earth. And there's clearly a difference here if you take a look at these arrows. These arrows are kind of pointing in 360 degrees of direction. These are generally pointing in one direction. These tend to get wider spacing as you travel further away from the Earth. These generally keep the same spacing. Now, if you remember, this is essentially the classroom that you're sitting in, and this would be the planet Earth. Now, when you zoom out and you consider the Earth to be what we call a point mass, or a mass that's located at one point in space, it's all concentrated at that one location, that's where you get a field that looks like this, where as you move away, you see a decrease in gravitational force. The line spacing gets bigger. You have arrows pointing in every direction. The classroom, while it is on the surface of the Earth, if you really just zoom in and you look at one small section, if you notice in this little box, these arrows are generally the same length, the same spacing. There's really not that much of a difference. And that's what we call this uniform field. And I call it uniform with quotes because technically, if you look at what's going on here, yes, the bottom of these arrows, the spacing down here is slightly less than up here. So technically, the force of gravity pulling on your head is slightly less than the gravity pulling on your feet because your feet is closer to the Earth where these arrows are closer together. However, within the classroom, that difference between the ceiling and the floor is so negligible on the scale of what you'd actually be calculating that we consider this to be a uniform field and we assume that everything is constant. Over here, we can't quite do that because there's clearly a big difference between looking at the Earth as one point in space and looking at one small region in which we can consider it, like the classroom, to be a uniform field. And the reason I point that out is the mathematics behind these two are a little bit different. We're very well versed with the mathematics behind things that go on in the classroom. We now have to adjust our understanding to point masses, not just uniform fields, objects in space such as planets, asteroids, suns, stars, things like that. So the uniform field that we've looked at so far has dealt with the force of gravity being Fg equals mg, and the potential energy gravitationally being mgh. That's something we're all familiar with. The one thing I'd like to point out is that if you notice, the potential energy is quite simply just the force of gravity times the height. And that's just because, just like work is a change in energy, it's force times distance, while the force of gravity times some distance will give me that change in energy. So it's important to note right now that you can certainly accept for now that Fg has always equal to mg and Eg equals mgh, but just realize that Eg is essentially just Fg times h. Well, if we want to take that same concept and apply it to a point mass, we have to not use Fg equals mg, we have to use Newton's universal law of gravitation, which we now know is gmm over d squared. Now going back to our uniform field, if Eg is just Fg times h, or the height, the same concept applies here. It's just, I'll call it distance instead of height because it's the distance from the center of your object. But if I take my force of gravity and I multiply it by that height or that distance, you'll just cancel out one of those distances and you just get gmm over d. all I did was took this force of gravity, multiplied it by the distance, and I wound up canceling out one of the distances on the bottom. So the same concept, slightly different equation. And again, it's all based off of this governing equation. So how does any of this apply to anything that we're going to look at? Well, if we take a look quickly at a few examples, if I want to analyze the force in a gravitational field, there's a few questions I can ask. But I'll start with this one. Let's say I have an 80,000 kilogram object just kind of floating around in space, and I want to know at this location right here, location A, that's 50 meters away, what can I find out about the force at that location? Now, there's no object here, it's just a point in space. Well, if it's a gravitational field, I can say, well, let me test it out with a mass. So if I grab a 3,000 kilogram mass, let's say I just happen to have it lying around, and I place it at that location, well, now I have two masses and I have a distance. I can certainly figure out my force of gravity. So Newton's universal law of gravitation would tell me that this 3,000 kilogram mass has a very, very small gravitational force of 0.00006403 newtons. So using the universal law of gravitation, I can find the actual force that's pulling on that 3,000 kilogram object. Now, it's also the same force pulling on the 80,000 kilogram object, because for every action, there's an equal and opposite reaction. The 80,000 kilogram object pulls with this much force on this guy has to pull with this much force on this guy. But basically, you can certainly calculate the actual force that's acting on that specific mass. That 3,000 kilogram mass is experiencing that force. If I place another mass there, it will not have this specific force. Okay, so the force of gravity, that specific force that acts on a mass. But more importantly, what if I wanted to know how much force per unit at location A did I get? Well, if my force of gravity was this, and I know that I had 3,000 kilograms, much like we did with field location A, I get 0.000000002 newtons per kilogram at that location. So what I can actually find is not the actual force on a specific mass. I can find how much force per kilogram I will get at that location when a mass is placed there. So hopefully this is starting to sound an awful lot like those field potential discussions that we've had. But you're basically looking at the force of gravity being the actual force acting on a specific mass, and what we call the field strength being the amount of force per unit or per kilogram at location A. So one is an actual force obtained when I place a mass there, and the other is just a description about a specific point that will give me information regarding what will happen regarding force when I place an object there. So the more technical definitions would be that gravitational force is the actual force experienced by a specific mass when it is placed in a gravitational field, and that's measured in newtons. And the gravitational field strength, which is actually a little g. We've always just kind of called that gravity, but more importantly now, it's the gravitational field strength. It's how strong that force of gravity is at a given location. And it's the measure of how much force will act on any mass when placed at a given location based on how many kilograms that object has of mass. So one of them is an actual force for a specific mass. The other is kind of a measure of how much force you'll get for any mass when placed at a location. So gravitational field strength tends to be a little bit more useful because I can apply it to any mass, whereas gravitational force is something that only a specific mass can possess at a given moment. If I wanted to calculate those, we've kind of seen these before, but the force of gravity universally is Newton's law of gravitation. How did I calculate G? Well, if it's just the force divided by the mass of your object, I simply just took this equation, divided it by mass, and wound up with gm over d squared. So I've divided out the mass that I placed there, and the other mass that's still in that equation is quite simply whatever mass I'm referring to. So in this case, the 80,000 kilogram mass. Now I can do the same thing with potential energy. I'll use the same exact example, the same location 50 meters away, but I'm no longer concerned with the force of gravity. I want to look at the potential energy in the field. So again, if I want to place my 3,000 kilogram object there, I can use my gravitational potential energy equation, but not the one for a classroom or a uniform field. I'll use my equation for anywhere in the universe, and I'll find that that object would have about 0.00032 joules of potential energy. And again, that's the actual energy obtained or acquired by a specific mass placed at that location. But more importantly, how much energy am I getting per unit or per kilogram at location A? That's kind of that field potential concept. So if I know the amount of energy I have and I want to divide by the number of kilograms I have, I'll take 0.0032, divide it by 3,000, and I will actually obtain the amount of energy per kilogram obtained at that location when any mass is placed there. So hopefully what I'm starting to get across is that whether I'm dealing with force, whether I'm dealing with energy, there's kind of this distinction between the amount of force I can have at a specific moment in time and the amount of force that any mass can have based on how many kilograms of mass it has, and the same with energy. A specific mass can have a specific amount of energy, but a field can also give me information regarding how much energy any mass will get at that location as a result of how many kilograms of mass it has. So again, if we take a look at that textbook definition, gravitational potential energy is the actual energy experienced by one specific mass when it's placed in a field, and that's measured in joules. And then there's this concept of gravitational potential, which is how much energy any mass will possess per kilogram when placed at a given location. And mathematically, if we use our universal equation for the energy possessed, potential energy possessed by a specific mass, well, if I divide the amount of energy I have by the number of kilograms, I'm just dividing this equation by mass, and I'm left with gm over d. So the overall takeaway from this, I know there are some examples here, you can go back and look through them. I'll certainly answer any additional questions you have. But the main takeaway is that whether you're dealing with force or energy, the actual force and the actual energy are physical quantities that are possessed by a given mass when it is placed in the field. The gravitational field strength, or the gravitational potential, refers to the force or the energy that any mass will have when it's placed at that location, and the amount that they will have is entirely based on how much mass each of them consists of.